So for those of you unfamiliar with the bodies in the solar system, Titan is a moon of Saturn. It's the second largest moon in the solar system. It's one of the 4 bodies in the solar system that have thick atmospheres and therefore climates. Unlike Earth, while Titan's atmosphere is mostly nitrogen, Titan has no oxygen. It's got a few percent of methane, 0.1% hydrogen, and lots of organics. It has a hydrological cycle. Methane falls as rainfall. Titan's very cold because it's so far from the sun. The surface temperature is 94 Kelvin. It has a gravity about the same as the Earth's moon, and the combination of a dense atmosphere and low gravity makes it a particularly easy place to fly. We'll come back to that very soon. What makes Titan of particular astrobiological interest, and this has been recognized for 50 plus years, is that methane in the atmosphere can be photolized by solar ultraviolet, and there's also energetic electrons in the Saturnian magnetosphere that are particularly important in that they have energies high enough to break the nitrogen-nitrogen bond. And the combination of those two destruction processes leads to molecular fragments that recombine in myriad ways to yield literally thousands of different hydrocarbons and nitriles. These are what form the brown haze that makes Titan's atmosphere optically opaque. We've measured many of these compounds directly, flying through the upper atmosphere with the Cassini spacecraft between 2004 and 2017. We've measured them in the atmosphere directly with the gas chromatograph mass spectrometer on the Huygens probe. We know there are compounds with molecular weights of thousands in the atmosphere, macromolecules that are assembled from these fragments. And we can replicate some of this chemistry in the laboratory with sort of Urey Miller type experiments, and those produce this brown gunk that Carl Sagan named Tholin. But in astrobiological terms, this stuff is a dead end. There's no oxygen incorporated because oxygen compounds have very low vapor pressures in Titan's cold atmosphere. So something else has to happen for the magic to begin, if you like. Now, all that organic material, much of it solid, drizzles down onto the surface. Some of it is liquid, actually. Ethane and methane form lakes and seas near Titan's North Pole. But at low latitudes, a lot of this material seems to accumulate and form sand dunes, actually dunes as large as the biggest dunes on Earth in the Namib or Arabian deserts. As I say, we think this material is polycyclic aromatic hydrocarbons, some N-substituted PAHs, again, organically complex, but not by themselves astrobiologically interesting. But just as the Earth is too cold a place for molten rock, so Titan is too cold a place for liquid water. But that doesn't mean there can't be transient locations and times where liquid water is present. Specifically, there may be cryovolcanic features on Titan's surface, at least one of which is considered a pretty plausible candidate, and impact craters, where impact events occur. You can generate large amounts of melt, which in Titan's case is melted ice, is water. And when you do experiments in the laboratory to hydrolyze this Tholin material, this brown gunk, with water, you generate amino acids and pyrimidines and all these kind of interesting building blocks. Because in the aqueous phase, you can incorporate oxygen atoms into the chemical systems. And then what happens, nobody knows, because some of these geological structures like impact features, impact melt sheets, can take tens of thousands of years to freeze. And we can't get grants nearly that long to study how complicated the chemistry can get. So there's the results of these amazing, irreproducible experiments sitting around on Titan that we can go and explore in situ that are difficult to replicate in the laboratory on Earth. Titan has a very diverse surface. compositionally. We know from the Cassini data making this this map that there are these brown areas near the equator which are covered in sand dunes. The dark splodges near the poles are the ethane, methane seas, and there are ice-rich areas exposed, and for all we know, lots of other materials. The stuff that's particularly interesting, of course, is this prebiotic chemistry that may be associated with transient water exposures. And it's very difficult to be sure when you just drop a probe into a planetary atmosphere that you're going to land at the rock outcrop that is most interesting. There's some melt sheet that's exposed, or maybe a methane stream has gullied into some bedrock and exposed material. And what Titan does for us by having this low gravity and thick atmosphere is it lets us use area the Dragonfly concept came about. So it was proposed in 2016 and was down selected with a Comet sample return mission for further study a year later. And in 2019, NASA decided we would actually do this. New Frontiers is a class of missions in the NASA framework led by an individual scientist, so-called PI-led mission, principal investigator, but with obviously a large team. And the the scale of this operation is something like $1 billion, right? It depends which fiscal year you're talking about and whether operations costs are included. But it's a big enterprise. It's not the biggest class of mission, the flagship, but it is a formidable effort. The idea is that we'll enter Titan's atmosphere in an aeroshell, a heat shield, pop out and descend by parachute, just as the Huygens probe did, and then release to use rotors for powered flight, much like an airport gadget store quadcopter. We don't have any relay assets in orbit around Titan. We have to communicate with Earth directly. We have a dish basically that flips up and points at the Earth to send the data back to Earth. For a sense of scale, this thing is the size of the Perseverance Mars rover, a little bit bigger than a Mini Cooper. The principal investigator, Elizabeth Turtle, at APL is shown there with the rotor blades to scale. They're actually about the same size as the rotors of the Ingenuity helicopter, but what we do is pick the whole laboratory up and fly it around to sites of interest. There's no separate vehicle that flies away. The intent is that we'll use radioisotope thermoelectric generator, much like Perseverance or Curiosity. Titan being so far from the sun, it's just not practical to use solar power. And we exploit the so-called waste heat from the radioisotope generator to keep the internals of the vehicle warm. The ambient atmosphere is dense and it's very cold, and so things like our drill motors need to be heated before we use them. Let me go on to the scientific payload. So Dragonfly has 4 instruments. One is one I lead the development of, a geophysics and meteorology package. So we'll measure the wind and the pressure and the methane humidity. We also have a seismometer contributed from Japan. And the idea is to use Titan quakes to probe the thickness of the ice. Like other icy moons of the solar system, we believe Titan has an internal water-rich ocean. In Titan's case, it's below about 70 kilometers, the models say, of ice, but it could be 50 kilometers, could be 150. And seismic methods may let us measure directly how thick that is. There is this theme in NASA planetary science right now called ocean worlds, focusing on icy moons of the solar system like Enceladus, Europa, Titan. Ceres is another icy world, ocean world, but it's not an icy moon. Titan is actually the most accessible of them. Because of its thick atmosphere, it's much easier to deliver an instrumentation package to Titan's surface by heat shield and parachute than all the expensive rocketry that you need to land on Europa, for example. Beyond the weather, we have an instrument to measure the near surface elemental composition using gamma rays. So we can land somewhere and within a few hours determine whether it's carbon rich, nitrogen rich, whether it's icy, if there's a lot of oxygen present. We do this from the gamma ray emissions. Now, on previous planetary missions, this kind of gamma ray spectroscopy is done by exploiting cosmic ray excitation. The asteroids or the moon even Mars get hit by cosmic rays, and those create neutrons, which in turn stimulate the rocks to spit out gamma rays. Because Titan's atmosphere is so thick, actually the cosmic rays don't get down to the ground. So we have to bring our own neutrons with us, and we actually use a pulse neutron generator that's used in the oil industry, actually, to basically blast neutrons out and stimulate the gamma ray emissions. Technically, this neutron generator basically accelerates deuterium atoms to hit a tritium target. So technically, it's a fusion reactor. I mean, it's a very small one, but it's a fusion reactor, which I think is kind of cool. We'll have cameras, down-looking cameras, forward-looking cameras, panoramic cameras we can swivel around, and a so-called microscopic imager that will let us look, at the sand grain scale, to try and understand how some of these sediments are transported around, fluvially or by saltation to form dunes. And there's a couple of neat little tricks we can do. The illumination on Titan is very diffuse. This haze scatters the sunlight and only basically lets red light down to the ground. But we can illuminate the scene, as some Mars rovers do with their microscopic images, with LED arrays to use specific wavelengths that may be compositionally diagnostic. So there's the picture on the right is a sort of false color image going a little bit into the near infrared, exposing different sort of flavors of tholin. And many organic compounds are fluorescent, notably quinine in your gin and tonic at a nightclub. The UV illumination stimulates an optical emission, and obviously different molecules fluoresce at different wavelengths. So at nighttime, we can use ultraviolet illumination to see if the dunes glow in the dark, which would be kind of fun. The real chemistry is investigated in depth with a mass spectrometer from our colleagues at Goddard Space Flight Center, the same outfit that built the Huygens GCMS and the SAM instrument on Curiosity. The mass analyzer is actually an ion trap mass spectrometer, so the same type that's been developed for MoMA on the ExoMars rover, which I guess is earthbound for another year or two at least. It uses a laser desorption front end, which lets you release high molecular weight organics from a target without destroying them. Right, the laser pulse kind of volatilizes the material without pyrolyzing it. So that lets us explore the higher molecular weight materials, of several hundred AMU to really start to see what kind of chemistry has been developed in the Titan surface materials. There's also a pyrolysis and gas chromatograph front end, and we can do the trick that's been employed with Curiosity of adding a derivatization agent that allows things like amino acids to go through the system through an enantioselective column. So we can establish whether there is, whether the compounds like amino acids are racemic, or whether there is a preferential selection for left or right-handed stereoisomers. And that's of course a property of living things. I always forget which way around it goes. So all the amino acids we use are left-handed ones and all the sugars are right-handed, or maybe it's the other way around. But there is this preferential selection in living things that is in principle not specific to the accidents of terrestrial evolution. I mean, the specific choice that life on Earth made would be interesting to see on Titan. It would be even more interesting to see selection, but in the opposite sense. There are other chemical signatures of life-type chemistry. For example, if you look at the mass distribution of fatty acids in animal products like sheep lanolin. All the compounds are have even numbers of carbon atoms because they're assembled from a building block that's got 2 carbon atoms in it. So you get a very non-random, let's say, distribution of molecular weights, and that's another signature we can look for. Of course, one challenge is how to get material, particularly from a cryogenic environment, into the instrument to do these analyses. And we actually use a rather interesting system developed by colleagues at Honeybee Robotics in California. We have a drill with a suction system. So basically the drill cuttings get pulled through, exploiting the Titan atmosphere, get pulled through a network of pipes into a little cup that then goes into the mass spectrometer instrument. We can just use a valve to decide whether to use the drill on the left skid or the right skid of the lander. This mock-up, the so-called Iron Bird, is full size, just for reference. I guess there's not actually a person standing next to it, but it's a big beast. It's like this tall. We intend to visit a place on Titan, basically on the anti-Saturn face of Titan. Titan is tidally locked like the Earth's moon, so longitude and the presence of Saturn in the sky are correlated. So sadly, we're on the anti-Saturn side, so Saturn is always below the horizon. There won't be any dramatic views of Saturn in the sky, sadly. But the reason we aim there is one part to do with the arrival velocities and the aerothermodynamics of the heat shield, but in particular because there's an impact structure called SELC, a crater about 80 kilometers in diameter, that has a lot of water-bearing, ice-bearing material exposed. Just to the south of it are these sand dunes, which we believe will have nice, safe places to land in the plains in between. The sand migrates across the interdune plains to form the dunes, and it can only do that because the interdune plains are nice and flat. So they're perfect places to make our first landing, and then we'll have aerial pictures and a lot of high-resolution data upon which to select the next place to go. This picture just shows terrestrial analogs of dunes, the same morphology and same size as those that we see in the Cassini data at Titan. You can see nice big flat plains next to them. The sand material will, of course, itself be of interest, but perhaps not. There's no prior expectation of particular astrobiological interest in the sand. The really interesting stuff will be associated, we think, with the impact crater. We can do a number of different flights. I mean, we have to fly, in fact, to land safely the very first time, which is going to be a tense moment. We basically spend the Titan night. Titan goes around Saturn once every 16 days. And so for 8 days of that, our landing site is on the side of Titan away from the sun and away from the Earth, so we can't communicate. So during that 8 days, we'll listen for Titan quakes with the meteorology package, of course, but we're basically charging up a big battery with the output from the radioisotope generator. With that energy, we can fly for about half an hour. We fly at about 10 meters per second. So we can maybe accomplish something like 12, 15, 18 kilometers net range. What we'll typically do is kind of fly 2 steps forward, 1 step back. After we've identified a potential future landing site based on safety and scientific interest, maybe 4 or 5 kilometers away, we'll overfly it and scout out the next site, and then come back to this site that we've scouted. So after the first landing, we never need to commit to landing anywhere that we haven't checked out first. So that's the basic scheme of operations. We'll do 1 or 2 profiling flights, flying to a couple of kilometers altitude to measure the structure of the atmosphere and how the flow over the dunes is modified by that. And there's some other things we'll do. We can also do little short hops to get nearer to specific outcrops of interest. So there's a lot going on. We were selected, as I mentioned, 3 years ago. NASA has taken a while to build up activity because of the various budget impacts of the COVID pandemic, among other things. But we're doing a lot of simulation work to understand the flight performance of the vehicle, which is beautiful in its own way. It's kind of a Frankenstein's monster. If you're an aerospace nut, you want a nice pointy vehicle that's streamlined and can fly very efficiently. That design direction is antithetical to the people who design drills, right? You don't typically have flying machines that want to put lots of weight on a drill bit and extract surface material. And of course, we've got this high gain antenna that we need to direct to the earth. So this is a thoroughly unique vehicle from an aerospace engineering perspective. We are actually able to do some wind tunnel experiments to validate the computer models we're using to assess the flight performance. There have been some challenges during the pandemic with access to some of those unique facilities. One great thing about a rotorcraft, in contrast to a rocket lander, is you can fly a prototype. Okay, we can't fly the whole 900-kilogram Dragonfly vehicle on Earth in Earth's gravity, but we can make a 0.56 scale vehicle and offload it to the point where we carry the same guidance equipment, the same camera and LiDAR for hazard detection, and we fly this out in the California desert over dune terrain that we think is representative of Titan. Of course, there's no GPS on Titan. We have to rely on this optical navigation. In fact, in many ways, it's rather similar to what's used on the Ingenuity helicopter. The development is proceeding. We are coming up on our preliminary design review later this year, and subject to that, we'll be developing Dragonfly for launch in 2027. It then takes us a little over 6 years to get to Titan. Outer solar system exploration is not an enterprise for those of you seeking instant gratification. But I started my career working on the Huygens probe at the very beginning of that project, and I'm very fortunate that we get to exploit that experience and go back to Titan. It seems like a long time in the future, but in fact, it does work through quickly. The nominal mission is for 3 and a bit years of exploration, during which time we expect to traverse something like 150 kilometers from the initial landing site to the crater, and then we'll be poking around, looking at outcrops and figuring out the best things to drill. So it's a big adventure. As I say, you can follow us along on the web, and I'm happy to take questions. Thank you.
Thank you for that talk. Very entertaining, very nice to see you fly back to Titan. There have been online questions as well. So think about questions from the audience now, and I'll ask some of the online questions first. Think about it. So there's a lot of questions from Daniel as always. So can you talk something about the geologic activity of Titan? Are there methane cryovolcanoes, so methane ice volcanism, that Dragonfly might encounter and might have the ability to fly through or something? Or would that be just no, far too dangerous?
Right, so you see that there's a diverse range of spectral properties exposed at the surface. Back when I started working on Titan, just an orange ball, we got the first maps from the Hubble Space Telescope. Titan was 18 pixels across, and there were bright areas and dark areas. And up to that point, the paradigm had been, as we suddenly stopped sharing, the paradigm had been that this photochemical material is formed in the atmosphere and drizzles down everywhere. So the surface should have been uniform in its color or albedo or whatever. Sure, yes. And that's clearly not what Titan is like. Something is moving stuff around. There are preferential accumulations of different materials. Most obviously, the dark material that makes the dunes is forming this equatorial belt. Now, we saw with the images at the Huygens landing site that there were tumbled, rounded cobbles. That's a process that requires fluvial transport. And the way Titan's weather seems to work is that basically the rainstorms follow the sun, that you have a lot of clouds and storms during polar summer and equatorial spring. The landing of Dragonfly will be at low latitudes during southern summer, same as Huygens, in fact. So we don't expect any methane rainstorms during our mission. As for volcanic constructs, the one putative cryovolcano that merits serious consideration is called Du Mons, and it's I don't know if I can see the pointer. Yeah, it's over here, right at the extreme left of the map, near the subsaharan. Is over here. So there's no known methane spring or cryovolcano near the Selk impact structure where we're going to go. Could there be a spring or something at smaller scale? Maybe. We would, because we have the opportunity after the first landing to scout future landing sites, we shouldn't encounter any geological structure by accident, right? We should know if there's a honking great volcano or a lake or whatever it is. We'll have some sense of that, and we would I expect to have very extensive discussions about each landing site, balancing hazard or perceived hazard against the scientific value, right? Usually the most interesting places are also the most dangerous. So you have this sort of dynamic tension between the engineers and operators and the scientists.
You just mentioned the rainstorms that are probably not likely during the time of landing, but I guess they will come back at some point during the 3 years of operations or so. And especially as soon as the weather is kicking in and it's not just bright sunshine, but rather thunderstorms or maybe potentially even thunderstorms, lightnings, and follow up on lightning chemistry. Are you very much looking forward to that part, or is that rather like hopefully you don't get that much lightning?
Yeah, so that's an interesting question. I actually did the lightning hazard assessment for the Huygens probe. While there is methane clouds and definitely rain, I mean, we actually saw during the Cassini mission clouds near the equator, near equinox, and we saw the ground in that area get darker and then get brighter again over subsequent weeks, suggesting that the ground was wet with liquid methane, and then it dried up. So there is an active hydrological cycle, but in all the 127 close flybys that Cassini made, it has not detected any radio emission from lightning. And in the one flyby of Earth that it made on the way out to Saturn, it detected thousands. So there is, while charge separation and lightning discharge isn't impossible with liquid methane. I mean, I've literally done the experiment of turning a propane cylinder upside down and spraying the liquid out, put a voltmeter on it, and you do get charge separation. And this is a consideration for aircraft refueling as a hazard. It's a priori unlikely insofar as the low dielectric constant and the low energetics of the whole system make lightning less likely. So we haven't seen any evidence for it. We don't know that it's impossible. We do know that the cloud activity, the convective generation of condensates only occurs at the pole during summer and only at the equator during equinox, which is like 2040 or so. So for the duration of the mission, we don't expect any lightning activity to be close to us. We have considered triboelectric charging, right? The downwash of air from the rotors, we expect to kick up some sand. In fact, we'll do that deliberately. We'll spin the rotors up at progressively higher speeds to see and watch what wind stress the sand starts to move. That's an important parameter in decoding what the orientation and shape and size of the dunes means in terms of Titan's paleoclimate. Right? How long do you need the wind pattern to prevail to build up dunes of this size? In fact, what we think happens on Titan is an analog of the Kroll and Milankovitch cycles on Earth, where the changing orientation of the pole with respect to the eccentric orbit around the sun means the seasons are of unequal length. Southern summer is shorter but more intense than northern summer. And that is probably not coincidental that all the liquid methane, all the seas on Titan are near the North Pole. We actually think that 50,000 years ago, the opposite was true. All the liquid was at the south. So there is this sort of different manifestation of astronomical climate change on Titan. And that also probably has an imprint in the dune pattern. But understanding that needs you to figure out what kind of wind stress you need to blow the sand around. And so we're going to fire up the rotors to do that. When that happens, we expect maybe some of the grains will become charged, and we'll measure that. We had to do a quick study to see if there would be like a really large charge buildup. You watch the movie Hunt for Red October. There's a guy dangling down from the helicopter getting onto the submarine. It's like a kind of lightning discharge, which is a thing that happens in rotorcraft operations. So we had to check that out. Looked at conductivities and capacitance and so on. And we're not worried, but we're paying attention to that sort of thing.
Fascinating. Questions from the audience? Yes, there's a question.
If I heard you correctly, you said that there are liquid water exposure from impacts that last up to 10,000 years.
Yeah.
Is that strictly from the kinetic energy that it melts the water, or does it crack the surface and it's released from the interior ocean?
Interesting. Yeah, so there is one impact structure on Titan called Minerva, which is 440 kilometers in diameter. And there was some modeling work, hydrocode work, just in the last year that looked at whether that might be large enough to actually allow material from the internal ocean to breach the crust, basically. And I think the answer is maybe, but that structure is probably a couple of billion years old. It's quite exceptional. For cell, it's basically kinetic energy buried in the target by the impact event itself. So to set it in context, the Sudbury impact crater in Canada is about the size, maybe a little bit bigger, and is the site of the world's richest nickel deposits, because it melted the rock and allowed the nickel and iron sulfides to basically sediment out. And you may get the same sort of fractionation processes in the melt structures here.
Do you have an estimate on the age of the self-crater?
No, it's one of the most fresh craters, though. A lot of the craters on Titan are degraded substantially, as is also true for most impact structures on Earth. The fact that you have a somewhat square rim probably reflects underlying faults. That's the case for meteor crater on Earth. It's also kind of square. But basically, it's still pretty well exposed. The depth is, we have radar measurements to say it's 200 or 300 meters deep. So it's not been completely filled in by blowing sand, which many of the structures are. Could I tell you it's 50 million years versus 200 million years? No. Sorry.
Yeah, thank you very much again. We are precisely at 1 o'clock now, so thank you for your talk.